Given A and V, we need to determine whether V is in core A. This is equivalent to checking whether the equation Ax equal to V has a solution. Step 1. Form the augmented matrix. Step 2. Use row operation. Make the entries below the first pivot 0. So row 2 equal to row 2 plus 3 over 4 row 1, and row 3 equal to row 3 plus 1 over 2 row 1. So result is minus 8, minus 2, minus 9, and 2, and 0. And row 2 is 0, 5 over 2, 5 over 4, 5 over 2. Row 3 is 0, minus 1, minus 1 over 2, minus 1. Multiply the third row by 5 over 2 and add it to the second row. Is row 2 equal to row 2 plus 5 over 2 row 3. Row 3 equal to row 3 plus 2 over 5 row 2. So we get minus 8. Row 1 is minus 8, minus 2, minus 9, and 2. Row 2 is 0, 5 over 2, 5 over 4, and 5 over 2. Row 3 is all 0. So the system is consistent and has at least one solution. So Ax equal to V has a solution. Exercise 20. Check whether the vectors are linearly independent. Given V1 equal to 1, 1 and V2 is 1 and minus 1. So place them into a matrix 1, 1 and 1 minus 1. So perform row reduction. Row 2 equal to row 2 minus row 1 is equal to 1, 1 and 0 minus 2. There are two pivots, one in each column. Therefore, the vectors are linearly independent. V1, V2 are linearly independent. And given V1, V2, and V3, so create a matrix with these vectors as columns. A equal to 1, 3, 5, 2, 5, 9, and minus 3, 9, 3. So row reduce. Row 2 equal to row 2 minus 3 row 1. Row 3 minus 2 row 3. Row 3 equal to row 3 minus 5 row 1. So equal to 1. Row 1 equal to 1, 2, and minus 3. Row 2 and row 3 are 0, minus 1, and 18. Then row 3 equal to row 3 minus row 2. So the last is row 1 is 1, 2, and minus 3. Row 2 is 0, minus 1, and 18. Row 3 are all 0. So there are only two pivots, but there are three columns. Therefore, one vector can be written as a linear combination of the others. The vectors are linearly dependent. So V1, V2, V3 are linearly dependent. So V1, 1 and 1 minus 1 are linearly independent, and V1, V2, V3 are linearly independent.
Determine method when to use when the number of vectors equal the dimension of the vectors. 3D vector forming a 3 multiplied by 3 square matrix. Core concepts. If the determinant is non-zero, the matrix is invertible, implying only the trivial solution exists. The vectors are linear independent. If the determinant equals 0, the matrix is not invertible, implying infinitely many solutions. The vectors are linear independent. Problem 1. Using the determinant method, set up the vectors 1, 2, 1, minus 1, minus 1, 2, minus 1, 0, 5 as a 3 multiplied 3 matrix A. Calculate the determinant expanding along row 2 for the 0. State A equal to 0. Since state A equal to 0, the set of vectors is linear dependent. Problem 2. Performing row operation. Set up the matrix using the 3 vectors as a columns. Use the pivot 1 in the first row to clear all the numbers below it in the first column. -3 to 1 to 0. Final analyze. Column 1 and 2 and 3 each contain a pivot position 1, -1, and 9 respectively. This means there are no free variables in the system. x1 v1 plus x2 v2 plus x3 v3 equal to 0, meaning only the trivial solution exists. Conclusion. This set of vectors is linear independent.
Now I will explain exercise 22. In this exercise, we are asked to determine whether the given 3 vectors are linearly independent or linearly dependent. The first method we use is the determinant method. First, we place the 3 vectors into a 3 by 3 matrix, with each vector becoming one column of the matrix. Next, we calculate the determinant of the matrix. To make the calculation easier, we expand along the second row because it contains a 0. This reduces the amount of computation. The determinant is calculated as the determinant of A equals -2 times open parenthesis -5 minus -2 close parenthesis -1 times open parenthesis 5 minus -1 close parenthesis, which becomes 6 minus 6. So the determinant equals 0. Since determinant equals 0, the matrix is now invertible. According to the determinant theorem, if the determinant is 0, the vectors are linearly dependent. So our final answer is the 3 vectors are linearly dependent because the determinant of the matrix is 0. Exercise 23. Definition. Basis. A minimal spanning set for a vector space. To form a basis, a set of elements must satisfy 2 conditions. 1. They must span the space. 2. They must be linear independent. Dimension property. The dimension of R2 plus 2 is 4. Since we are given exactly 4 matrices, if we prove they are linear independent, they automatically form a basis and must span in space. This problem uses a different method called row reduction or Gaussian elimination. First, we arrange the 3 vectors as the column of the matrix. Then we perform eliminatory row operations to transform the matrix into row echelon form. Our goal is to create pivot positions by eliminating the numbers below each pivot. We first use the pivot in the first row to eliminate the entire below it. Next, we continue the row operations until the matrix reaches echelon form. After the row reduction, we observe the final matrix. We can see that every column contains a pivot position, and there are no free variables. Since there are no free variables the equation x1v1 plus x2v2 plus x3v3 equals 0 has only the trivial solution x1 equals x2 equals x3 equals 0. Therefore, the vectors are linearly independent. So our final conclusion is, because every column has a pivot and there are no free variables, the set of vectors is linearly independent. Final conclusion and answers. There are 4 non-zero rows, meaning columns 1, 2, 3, and 4 all contain a pivot. Answer to Q2. No free variables exist. The 4 matrices are linearly independent. Answer to Q1. 4 linearly independent elements in a 4D space will automatically span the space. Final conclusion. Since they are both linearly independent and span the space, these 4 matrices do form a basis for R2 plus 2.